Hello, my name is Nabil Bazi, and today I will present to you our recent work on digital twin architecture for mining industry, a case study of a stacker machine in an experimental open pit mine. First, we will present the state of art of the digital twin concept and the objective behind for using it in industry and in particular in mining industry. The proposed architecture of a digital twin will be presented secondly. Then we will talk about the case study of our work and the results achieved. A digital twin is a digital replica of an object, process, or system that can be used for various purposes. The digital representation indicates both the elements and the dynamics of how an Internet of Things device functions over the course of its lifetime. A digital twin also incorporates historical data from the past use of the machine that it incorporates into its digital model. Digital twins are utilized in a variety of industries to improve the operation and maintenance of physical assets, systems, and manufacturing processes. Digital twins are a formative technology for the industrial Internet of Things, where physical objects can live and interact virtually with other machines and people. The digital twin has several definitions, but it is best described as the seamless integration of data between a physical and virtual system in either way. Figure 1 describes the difference between digital model, digital shadow, and digital twin, and the digitalization levels of integration for each one of them. Thus, there are 3 levels of integration, which are characterized by the data flow exchange between the physical plant and the digital system regardless of being a digital model or digital shadow or digital twin. The proposed conceptual architecture of a digital twin. The conceptual architecture shown in Figure 2 presents the design of a 2-level digital twin, which is the digital shadow, that includes 4 layers. Layer number 1, physical layer. Layer number 2, data preprocessor layer. Layer number 3, edge computing layer. And layer number 4, cloud layer. As well as the digital threads depicted are used to characterize the digital twin's degree of maturity, either its traceability back to the physical assets requirements, parts, and control systems. Each layer will be described in detail in the second slide. Physical layer. Data must first be acquired from physical assets on the open pit mine until it enters into the digital twin framework. Layer number 2, the data preprocessing layer. Data preprocessing involves converting raw data into well-formed data sets in order to use data mining methods. Edge computing layer. Edge computing is processing that takes place near a system's data or end user where information is coming from or going to. By minimizing latency and lag, edge architecture enables for faster processing. The last layer. The layer number 4 is the cloud. The cloud layer here, the last layer of the digital twin, it is the cloud layer which is characterized by hosting the cloud database, the main database that receives data from the previous layer for either storing and feeding the virtual mine and its optimization and predictive data applications. including predictive production and maintenance scheduling, process optimization, supply chain, and predictive shift work scheduling. Here it comes to the case study. So, to answer the question of why choosing the Stacker machine, it is highly considered that the value chain of the experimental open pit mine is characterized by a production line which is equipped with several mining equipment. And at the end of the product production operations, the storage machine stacker allows to store the final product according to the quality of phosphate in the suitable stock as shown in the figure number 3. The stacker process characteristics presented are taken into consideration while developing the digital twin in order to study the behavior of different components and its impact on the production and the maintenance main key performance indicator, maintenance KPI. The goal is to control the automatism in the simulation in parallel with the real case study and compare these different behaviors and test critical scenarios. Thus, the process of the stacker machine is composed mainly by 5 major operations, which are: first, start conveyor, translation, rewinder, boom lifting, and boom lowering. The work presented is a significant approach toward the design of a digital twin of the Loudon Park stacker machine. It is a digital twin that faithfully represents the operative and control part of the automatism as well as the mechanisms, actions, orientation, displacement, and lifting of the boom, with a real link with the PLC of the system. The digital twin in its first level, which is based on a digital simulation of the real process through a software solution dedicated to the simulation of automated systems, electrical diagrams, machines, and processes. Thanks to a patented modeling technology, it allows users to design and provide realistic virtual systems to test the design and control of real systems. It is a simulation environment for automated systems with virtual modules available and configurable for connection to PLCs. So, we could sum up the main outcomes of this work by these 3 points. Purpose of commissioning and validating the control command system program. Checking compatibility of modules before the implementation on the field. Simulate the critical behavior of the process. As a conclusion for this presentation, we could see that there are 3 highlighted conclusions, which are the conceptual architecture that shows up the details of the design of digital twin, particularly in the mining industry, representing the benefits of using that technology, the digital twin technology, to reduce many challenges faced in the mining industry. A digital twin which integrates many applications and services that encapsulate the digital threads according to each level of maturity of using basic, full, enhanced, and the next generation. And the design of a digital twin which is based on a digital simulation of the real process through a software solution dedicated to the simulation of automated systems. And as a future work of this presentation, we have 2 points to highlight. First, enlarge this work by developing the digital twin of the other equipment that constitute the production line of the experimental open pit mine, and reform and revise the applications and services presented in each layer by focusing on many research points. These are the references of our work. And thank you so much for your attention.